So I've titled this Molecules Are Strange. Again, I have failed to change the term on the PowerPoint slide. It says fall 2021. This is, of course, not fall 2021, thank goodness. But it's just I haven't changed the title of the slide, so I didn't look very closely at it. But yes, we're calling this Molecules Are Strange. And they're strange for reasons, and we're going to talk about that in a minute. Now, why are molecules strange? You don't need to take notes on this. Let's just think for a minute about why molecules might be strange. Well, the core reason why molecules are strange is that they're very small, right? They're not that small when you compare to like a proton, right, which is inside of an atom, but they're still quite small. And the reality of the way that physics works is that on very small scales, the universe starts to do things that is not totally natural to our minds. And there's a reason for that, which is that, 200, 300,000 years ago, however long it was when our minds were evolving and developing, they were not, let me emphasize, were not evolving to understand this stuff. That was not the primary concern at the time, believe it or not. And so when we get down to this really small stuff, sometimes it's a little counterintuitive, some of the stuff that we're going to learn, right? And that's okay if it's a little counterintuitive, because I'm telling you, as somebody who's been studying this for a long time, it's still a lot of it counterintuitive to me. But we're going to do our best to try to build models that know about, that can figure things out anyway, even though some of the details might be a little bit counterintuitive, right? And some of the weirdest details in this class are what we're going to see today, but because of that, we also have some of the most straightforward, like step-by-step things that you can do to sort of get through the weird parts and get to the final answer. Okay? So that's what we're going to be working on today. We're going to be talking about molecules, but as always, let's take a minute to talk about last week. So what did we do last week? We started with this thing called the particle model of bond energy. And the basic idea behind the particle model of bond energy is hopefully, something that you sort of are willing to accept, which is that if you know how many bonds you have, and you know how much energy is in each of those bonds, you can calculate the bond energy of a substance, right? It's just the number of bonds you have in your substance multiplied by the energy in each bond. That's all that this is. And what we said was, in a solid or liquid, well, mostly solids. We're not really going to talk about liquids much in the particle model of bond energy, so let's just talk about solids. In the particle model of bond energy in a solid, it turns out that on average, each atom is going to have around 12 neighbors. And what we said was that those 12 neighbors are going to provide most of the bond energy. Now, will the molecules be bonded to other molecules somewhere else that are farther away that have less bond energy? Yes, they will. But we're not going to worry about that for this model. We're just going to worry about the particles that are close by. And on average, each particle if you have a large collection of them that are all bonded together, they're going to have about 6 neighbors. And when you add it all together, you get this, that the bond energy is equal to -6 times the number of particles times epsilon. Now, one thing that I want to point out is that this is a negative energy. Right? This is a negative potential energy. Why is bond energy negative? Because of the way we draw the Leonard-Jones potential at the end of the day. It's because of the way that we draw the Leonard-Jones potential. And the idea is, if you want to break particles apart, right, so you have a bunch of particles that are held together by bonds, you want to break those bonds and push the particles apart, you have to increase that bond energy up to 0. That's what we call a gas. A gas is a collection of particles that have 0 bond energy. In other words, the particles are not connected by bonds. And then we introduced this thing called the particle model of thermal energy. And we're not done with it. We're going to talk about it more today, but this is the particle model of thermal energy. And it's all built around one interesting idea. And the important idea is this piece right here. Whoops. It's this. Right? That every particle or every mode in a substance is always going to have the same amount of energy. And a mode, as far as we're concerned, is just a box that thermal energy goes into. Why do these modes exist? We don't know. The details are not super important for what we're going to do. I'm sure you could look them up. There's interesting stuff out on the internet about this. But for our purposes, the important thing is that when you have a substance, it's going to have a certain amount of these thermal energy boxes, and each thermal energy box will always have the same amount of energy. It's this, 1/2 kBT. This fact is known as equipartition. You do not need to know that word. If you do happen to know that word, great, but you don't need to know it. It just means that the energy is being equally partitioned or equally split up between all the modes in the substance. Okay. And what we found was that in a solid or liquid, that there are, in solids and liquids, there's usually going to be 6 modes per particle. We didn't really say why, though, so let's do that here. We have 3 kinetic energy modes and 3 potential energy modes for substances in a solid or liquid. Why? Well, there's actually two questions here. The first is, why is it 3? And the second is, why do we have kinetic and potential energy modes? So let's start with the 3. Why is there 3 of each? Well, the reason is that it's actually either very simple or very deep, depending on how much you want to think about physics, is that we live in a 3-dimensional universe. We live in a 3-dimensional universe, at least 3 dimensions of space. There's a dimension of time, but let's not worry about that right now. That's not important. What do we mean by saying that we live in a 3-dimensional universe? Well, what we mean is that there are basically 3 directions that we can move in. And those directions are up and down, left and right, and front and back. And any other direction that you might like to move is going to be some combination of those 3. Right? Every direction that you want to move is some combination of those 3 directions. That's what it means to say we live in a 3-dimensional universe. Could I imagine a 4-dimensional universe? No, not in my head. We can imagine it mathematically. That is something that we can imagine mathematically. Again, I have no idea what living in such a universe would look like, but it could exist. And if that was the case, and the laws of physics were otherwise mostly the same, then we would expect that we would have, in a solid or liquid, we would have 8 modes, 4 potential and 4 kinetic energy modes. But we don't live in a 4-dimensional universe. We live in a 3-dimensional one, so we end up with 3 and 3. So that's the first part. And the second part is, why 3 kinetic energy modes and 3 potential energy modes? Why is that? And the reason comes from thinking about, oops, too far. The reason comes from thinking about what's happening in the substance that causes them to have thermal energy. Right? So in solids and liquids, particles are bonded together. Right? That's what it means to be a solid or liquid, is there's bonds between neighboring particles. In liquids, the bonds are a little weaker, and the particles kind of move past each other a little bit easier than they can in solids. But nonetheless, there are bonds. And let's just imagine 2 particles in that substance. Imagine you have a whole substance with tons of particles, but we're just going to focus in on 2 of them. If those particles are sitting in the bond, they're never going to be sitting still. They're always going to be bouncing back and forth a little bit. That's just the way the universe works. Everything's always vibrating a little bit. And that is a lot like a mass on a spring. It's kind of just bouncing back and forth forever. And that is, when we think of thermal energy, it's that bouncing back and forth that we're thinking of. But of course, the particles are still in a bond. So just like with a spring, they're taking kinetic energy and converting it to potential energy, and then back to kinetic energy and back to potential forever and ever and ever. So you have this exchange between kinetic and potential energy. And so we end up with both kinetic and potential energy modes. Right? These are separate from the potential energy that's in the bond energy. That's something else that we learned about. It's just that because these particles are bonded together, there's always this bouncing back and forth. Much like a spring, you have some kinetic and some potential energy. So why 3 and 3? Because we live in a 3-dimensional universe. Why potential and kinetic energy? Because bonds are sort of like springs. Again, they're not exactly like springs, but they're sort of like springs. Okay. And what that leads us to is this. It leads us to the fact that in a solid or liquid, half of your thermal energy goes into kinetic energy and half of it goes into potential energy. But why? Again, the reason is that there are 3 kinetic energy bonds and 3 potential energy bonds for particles in a solid or liquid. Okay, so that's the solid and liquid case. And I promised last week that this week we would talk about the gas case. And that's what we're going to do now. Now, the gas case is more complicated. Right? With solids and liquids, it's easy. It's 3 and 3, because we live in a three-dimensional universe. If you were talking about something that was two-dimensional, it'd be 2 and 2. Four-dimensional, it'd be 4 and 4. But in a three-dimensional universe with a three-dimensional solid, it's going to be 3 and 3. With gases, it's more complicated. This is the thing that I was talking about that's a little more abstract. It's not as easy to sort of grab onto, but there's a nice thing about it, which is that this is one of the few things in this class where we can just give you a recipe that if you follow, you will always get the right answer. It's just a recipe. It's a step-by-step guide that you can follow that will get you to the right answer here when we talk about the particle model of thermal energy for gases. I've made a couple of videos on this over the last 2 years. There's at least one DL summary video that just talks about this, and then one of the short lecture videos that just talks about this. The short lecture video should be posted. The DL summary video is also, you can also find it. If you go to the DL videos link on Canvas, it'll take you to that YouTube channel, and you just search for modes or something like that. It should pop up pretty quick. It's a DL summary video. I don't remember the exact number of the DL, but it's there. So, of course, you will have this recording of this lecture. You'll have those videos. And again, this is just a recipe that we can follow. So the first thing we might ask ourselves is, why would gases be any different? Why would gases be any different? Well, the main reason is that, again, let's think about why we said there are kinetic and potential energy modes in solids and liquids. The reason was that you have bonds between the particles. Right? The particles are sitting there, they're bonded together, and they're bouncing back and forth in the bonds. In gases, we have a problem, because the particles are not bonded together anymore. That's what it means to be a gas. What it means to be a gas is that you're a bunch of individual particles flying around, not interacting with each other. Maybe very briefly, you might run into another one if you're really unlucky or lucky. You might run into another gas particle, but in general, the particles are not going to be interacting. And so we have a whole different scenario, and we have to figure out what to do with it. Now, of course, particles inside a gas themselves may have bonds internally, right? So, does anyone know what this molecule is? Do we know? CO2? That's what I'm hearing. CO2? Yeah. So for whatever reason, oxygen is red in a lot of these diagrams. Carbon is black. And so this is 2 oxygen atoms and a carbon atom is CO2. So this is CO2. And the CO2 molecule does have a bond inside of it, and 2 bonds, in fact. Well, 4 bonds, I guess, depending on how you're counting. We're not going to worry about those details. Don't worry about that. Right? But there are bonds between the carbon atom and the 2 oxygen atoms. But the carbon dioxide, this carbon dioxide molecule is not bonded to other carbon dioxide molecules because it's in a gas. And so we have to figure out something different about how to do this calculation. Before I go any further, I just want to be clear about what I mean when I say a particle. I want to be very explicit. The particle is just the smallest amount of the substance that you can have. So when I say a carbon dioxide particle, what I mean is 1 carbon dioxide molecule. You could zoom in if you want and think just about the oxygen atom or just about the carbon atom, but then you wouldn't be talking about carbon dioxide anymore. Right? So when I say a particle, I mean very specifically the smallest amount of substance that you can have. Now, in some cases, that might be an atom. Right? Some gases are just a bunch of single atoms flying around. Those exist. But most of the time, we're going to be talking about cases like this, where you have a molecule with 2, 3, maybe even 4 atoms in it. And we need to figure out how many thermal energy boxes this molecule has. And that's what we're going to do now. And this is the part where, like I said, it's just a recipe. So let's, actually, before we move on, let's go back. Let's try to think of a monatomic gas. Does anyone know of any good monatomic gases? So this would be a gas that's just a bunch of single atoms just flying around. I know one. Can anyone think of one? Someone in the last class said nitrogen. Helium? Is helium monatomic? Okay, so helium. The one I was thinking of is argon. But yes, helium is another good example. So let's think about a helium atom. Right? A bunch of helium atoms flying around. And let's ask ourselves, how many modes would those helium atoms have? Well, maybe if you think a little bit about what I said about solids and liquids, we can come up with an answer. Right? If you're a helium atom, all you're going to be doing is flying around. That's it. Right? You're just one little atom You have no bonds to anything else, not even other atoms, right? You're just one atom. And you're flying around in a three-dimensional universe, right? This universe is three-dimensional. And so it turns out that if you just had a single atom all on its own, flying around, like again, a helium, that atom would have 3 modes. Just 3. 3 modes because it can fly around in 3 different directions. And it turns out, so now we have 3 modes, 3 kinetic energy modes because the particle is flying around. Now let's imagine we grab a bunch of atoms and put them together into a molecule. And let's ask ourselves, how many kinetic energy modes would that molecule have? And the answer is, it will have the same number of kinetic energy modes as the atom started with. So if you have 3 atoms that are flying around on their own, each of those has 3 modes. 3 times 3 is 9. You put them together into a molecule, that molecule that you will end up with will still have 9 kinetic energy modes. This is just a rule about the way these things work for some reason. The details, again, have to do with, we live in a 3-dimensional universe and other quantum mechanics stuff, but this turns out to be how it works. And so there's actually only 2 pieces of information that you need in order to count the number of modes that a gas has, and it's these 2 pieces of information. You need to know 2 things. You need to know how many particles how many atoms are in your molecule, for the reason that we just discussed, and we'll discuss more in a second. And you need to know the shape of the molecule. But when I say the shape of the molecule, I actually mean a very specific thing. I do not mean like the specific shape of the molecule. All that we need to know is the molecule a line or not? Is the molecule a line or not? Is that my computer? It might have been my computer. No. My Discord's not open. OK. So all we need to know are how many atoms are in the molecule, just the number, and whether it's a line or not. If it's a line, we get one thing. If it's not a line, we get another thing. We'll talk about that in a second. OK. So this is what I already said, right? I said, let's imagine counting modes for this carbon dioxide molecule. Right? And what we said was that each atom brings along with it 3 kinetic energy modes. So this is called a triatomic molecule, right? There are 3 atoms in it. And that means that carbon dioxide will have 9 kinetic energy modes. But we have to do better than that. And this is why. Well, we'll see why in a little more detail over the next couple slides. But the reason comes down to these 3 things. Right? These modes are actually going to be split up a couple of different ways. And the way that they're split up is actually going to affect how many total modes the atom has, or the molecule has. Because it's going to have more modes than 9, actually. It's going to have some potential energy modes. And we have to figure out how we compute how many potential energy modes it has. So the first step, right, the first step in this recipe is take the number of atoms in the molecule and multiply by 3. That gives you the total number of kinetic energy modes. Easy, right? So this molecule has 3 atoms. Take 3, multiply by 3, you end up with 9. So we have 9 kinetic energy modes, but now we need to figure out how they're split up. So let's take a moment to just be clear about what those 3 words mean. There are 3 kinds of kinetic energy that a molecule can have. There's translational kinetic energy, rotational kinetic energy, and vibrational kinetic energy. Now, 2 of these we've already seen. Translation in physics just means moving from one place to another. Let's think about this. We know how to calculate the kinetic energy for an object that's moving from one place to another. We've done it in this course. We learned an equation. If I tell you the mass of an object, and I tell you how fast it is moving, you can calculate a kinetic energy. We know how to do that. There's just a nice little equation. It's the same kind of kinetic energy here. We're still talking about the kinetic energy that this molecule has because it's flying from one side of the room to the other. But we're learning now to calculate it in a different way, which has to do with modes. So that's the translational piece. Again, that's something that we can imagine, hopefully pretty easily. Just an object moving from one place to another. We see that every day. OK, what about the rotational piece? Well, the rotational piece is exactly what it sounds like. The molecule is going to be rotating. That is another kind of kinetic energy. It's a kind of kinetic energy that we have to take into account, right? It just turns out that this is the way, well, it's probably not that mysterious, right? Again, just like with translation, an object moving from one place to another, hopefully we can imagine an object rotating, right? We talked a little bit about rotational kinetic energy a while back. We didn't learn any details about it. We just said when objects rotate, they have kinetic energy. This is why. And then the last one is vibrational kinetic energy, and this is the tough one. And it's the tough one because it's just really hard to visualize. I'll have a slide about it in a minute here. But it's just really tough to visualize. So our first step is done. We know how many kinetic energy modes we have. The second step is to figure out how much of each there are. So let's start with the translational one because it's the easiest. Every molecule, every atom, every type of gas particle that you can ever imagine will always have the exact same amount of translational kinetic energy modes. Does anyone want to guess what the number is? Yeah, it's 3. Surprise. It's 3. Right? Why? Because the molecule exists in a 3D universe, in a 3D world. There are 3 directions the molecule can move. It can move up and down, it can move left and right, and it can move front and back. And any other direction that it moves is a combination of those 3. It's a combination of those 3. So that's the easy part. That's the easiest part, right? Every molecule has 3 translational kinetic energy modes. Okay, so now let's talk about rotational. This one is slightly more complicated, but hopefully not too terribly complicated. This is where the shape of the atom comes into play. Now, if you're looking at this, it's not probably at all obvious why this is true, right? So in the DL classroom, hopefully you've seen we have those the 2 red balls that are connected by a spring. That's the sort of model I want you to imagine in your head for this atom at the moment. Obviously, in a real carbon dioxide atom, there's another sort of atom there in the center, but let's just imagine, there's this bug that's lost. I don't know. Okay, well, anyway. Did you all, this is reminding me of something. I don't know if you all heard about this, but like 4 years ago at a school in LA, there was a graduation, and there were pelicans that were like dive bombing the graduation in the middle of the graduation. I don't know if you all heard of that. That was my graduation. It was this bug is much less annoying than a pelican, but they were literally, I don't know if they were confused or something, but they were like flying over the graduation ceremony and then like right down into the, it was weird. Look it up. It was wild. This is not quite as wild, but it is distracting still. So anyway. Okay, so why is it that a linear molecule has 2 rotational modes and a nonlinear molecule has 3? So again, think about this our sort of model of a molecule, which is those 2 balls connected by a spring. And I want you to imagine taking that model and turning it like this, right, around its long, right? You can imagine turning it like this, you can imagine turning it like this, but now imagine turning it like this. And what you'll notice is that, especially if you're sort of squinting at it and not looking too closely, it doesn't matter how much you turn it this way, it pretty much always looks the same. Right? It always looks the same. If you rotate it like this, it's going to look different. If you rotate it like this, it's going to look different. But if you rotate it like this, it's going to look the same, no matter how much you rotate it. And because of the mysteries of the universe, the mysteries of quantum mechanics, it turns out that if you have a molecule where you rotate it like that and it looks the same, that does not count as a rotational mode. So this is an example, right? This is a linear molecule, which means if we spin it in this direction, it's always going to look the same, and so that does not count as a rotational mode. This is why we need to know the shape. If you have a linear molecule like this, there are only 2 rotational modes, only 2 directions that it can rotate in, this way and this way. If you have a nonlinear one, though, it can rotate in this 3rd direction, which is like this. So this is an example, right? No matter which way you turn this, it's always going to look different. Does anyone know what this molecule is? Everyone's favorite. Yeah, it's water. Right, so hydrogen is white. Don't know why, but hydrogen is this white color in a lot of these diagrams. So this is 2 hydrogen atoms and an oxygen atom, or as we more affectionately like to call it, water. But the point is, it's a nonlinear molecule. Right? It doesn't have this, what we call this symmetry, right? So no matter which way you turn it, it's going to look different. It has 3 rotational modes. Okay, So where are we now? Well, we've got our carbon dioxide. We've determined that it has 3 translational kinetic energy modes, because every molecule has 3 translational kinetic energy modes. Every atom, every gas particle always has 3 translational kinetic energy modes. It has only 2 rotational kinetic energy modes because it's linear. And so then the question is, how many vibrational modes does it have? But we've sort of already answered this question, because we know how many total kinetic energy modes it has to have. We determined that already. It's 9. It's just 3 times the number of atoms. And so if 3 of those are translational and 2 are rotational, there's only a number that could be the number of vibrational modes. It's 9. So we figured out the total number of kinetic energy modes. It's 9. We figured out that 3 of those were translational kinetic energy modes. 2 of those are rotational. That leaves 4 to get up to 9. Those 4 must be vibrational modes. But there's sort of a special thing about vibrational modes. And to think about why, let's actually go back to remember what I was saying about the case of a solid or liquid, right? There were 3 translational kinetic energy modes, but also 3 there were 3 vibrational kinetic energy modes, but also 3 vibrational potential energy modes, right? Because there's some sort of bond that's vibrating. It's the same thing here. With molecules in a substance, whenever you have a vibrational kinetic energy mode, you must also have a vibrational potential energy mode to go along with it. So this molecule has 3 translational kinetic energy modes, 2 rotational kinetic energy modes, 4 vibrational kinetic energy modes, and because you have 4 vibrational kinetic energy modes, you must also have 4 vibrational potential energy modes, and that brings us to a total of 13. 13 for this molecule. So like I said, this is a recipe that you can follow. You're going to do it a few more times in GL, so I'm not going to do it all over again here. But this is a recipe that you can follow. If you know the number of atoms in your molecule, and you know its shape, right, whether it's a line or not, that's all I mean by shape. If you know those 2 pieces of information, you can always calculate exactly how many modes each particle has. And it turns out that there's a nice little equation that we can use that makes this much simpler. Now, you can't always use this equation, not because it will give you the wrong answer, but because it won't give you all the information that you need. And we'll talk about why that is in a little bit. But for a non-linear molecule, the number of modes per molecule is always going to be the same. It's going to be 6 times the number of atoms in your molecule minus 6. And for a linear molecule, it's going to be 1 more, 6 times the number of atoms in the molecule minus 5. And just to be safe, let's make sure it works, that equation works for this case. So this is a linear molecule with 3 atoms. So we use this equation right here, 6 times the number of atoms minus 5. 6 times 3 is 18, minus 5 is 13, which is exactly what we got. And so if you're in a situation where all you need to know is the total number of modes, this is a perfectly good way of doing it. Right? This is a perfectly good way of doing it. Now, I want to just take a little aside here to talk about the vibrational modes. So the particle, this is a nonlinear molecule, right? A nonlinear molecule has 3 vibrational kinetic energy modes and 3 a nonlinear molecule with 3 atoms in it is going to have 3 vibrational potential energy modes and 3 vibrational kinetic energy modes. And in this case, they sort of look like this, roughly. I can sort of visualize this, but what makes this weird is that all 3 of these modes are happening at the same time, which I don't really know how to visualize. But that's the way it works. So the point is, it's okay if you can't visualize the vibrational modes. Like, we can sort of do it with 3. Imagine doing it with 4, 5, 6, 7. It gets too complicated, right? The important thing to remember is not what the vibrational modes look like. It's just to remember that the number of vibrational modes is not going to be equal to the number of bonds. So this is a this molecule has 2 bonds in it, but 3 vibrational modes, right? So the vibrational modes are just weird, and we sort of can't do anything about it. But we know how to count them now. We know there's a recipe we can follow that will always get us the right answer for the number of particles in, or excuse me, the number of vibrational modes in the molecule. So why did we do all this? Why did we spend all this time talking about these modes? Well, there's a couple reasons. One of them we'll see here in a minute. Another one we'll talk about right now. When we were working with thermal energy at the beginning of this course, we did not ever calculate the total thermal energy of a substance, right? So I would say you have some water that is being warmed up from 20 degrees Celsius to 60 degrees Celsius. And you would then have an equation that would allow you to calculate the change in the thermal energy for the water, right? That's something that we did. What we never did was actually calculate the total amount of thermal energy that the substance has. We only ever calculated changes. But we can actually do that now because we know 2 things. We know some things about thermal energy. We know that thermal energy is split up into boxes, and we know that each of those boxes always has the same amount of thermal energy. And so there's only 2 pieces of information that we need in order to calculate the amount of thermal energy in our substance. It is the number of boxes, right, the number of modes, and the amount of energy that's in each of those modes. Or if we wrote it out a little bit more explicitly, it's the number of modes in each particle times the number of particles, gives us the total number of modes, the total number of boxes, and then you just multiply that by the amount of energy that's in each one, and you get the number. In this class, we're going to use the hashtag sign to represent the number of modes per particle. I'm old enough that I learned the hashtag symbol as the pound sign. It is on your phone. On the phone, it's called the pound sign. Apparently, it has some other really fanciful name. I don't know what it is, but it's some weird, really weird long name. But I'm just going to call it the hashtag symbol. It just means the number of modes in each particle. OK, so we're going to come back to all of that. But I'd like to take a moment to talk about something else, something that's not going to be on any quiz or any test, so you do not need to take notes on it. I didn't actually originally plan it this way, but this worked out really well, that this topic fit in really nicely with molecules are strange. So I want you to think back a couple of weeks ago. I was talking about how the universe is getting bigger. And I gave us one of the half of the story. And the half of the story I gave us was Henrietta Swan Leavitt's story. And what she discovered was how we could figure out how far away something actually is out in the universe, right? What she allowed us to discover was, or what she allowed us to determine, was how bright certain stars actually were. So we could say, well, we know how bright the star actually is, we know how bright it looks from here, and so we can figure out how far away it is. But in order to figure out the universe is getting bigger, there's another piece that we need. And the other piece that we need is how fast the object is moving away from us. And we didn't talk about that. And so that's what we're going to do now. So I'm going to first play you a very short video of something that you have probably seen at some point in your life. Or heard, well, more actually heard. You can't really see much in this. This is like 240p YouTube from 2007 or something like that. But you'll be able to hear it just fine. So what's going to happen to this? Presumably you've heard that at some point in your life, right? You go by, maybe not somebody, maybe not somebody honking a horn, but perhaps. The other thing that you sometimes hear is ice cream truck. I don't know if ice cream trucks drive around Davis very much anymore, so fun story. I was actually born here, lived here until I was 6, and then I moved away. But I do remember the ice cream truck that would come down my road. It was Cypress Lane. It's over by the Nugget in West State. I don't know, whatever. And sometimes you hear this with it's not as pronounced with the ice cream truck because the ice cream truck is usually going more slowly, but it's the same thing. When the ice cream truck is coming towards you, it sounds a certain thing, and then it passes, and the pitch gets lower, the whole thing gets lower, which, to be honest, would be a great thing for some really can you imagine the middle of the night and you hear an ice cream truck coming by, and as it goes by, the sound gets lower and lower? Yeah. ugh, not my thing. Okay, so we could imagine that. But why is this happening? Right? Why is this happening? Well, the reason has to do with the way sound waves work, which is this, is that if the object is, if the object is moving while it is releasing sound waves, then the waves in front of it are getting bunched up, and the waves behind it are being stretched out. We don't need to know a lot about waves for this class. You're going to study it in Physics 7C if you take Physics 7C. But hopefully you've heard at some point in your life that sound involves waves. It does. Is that thing still flying around? Oh, yeah, there it is. Sound involves waves, and when an object is moving, the sound waves in front of it get bunched up close together, and the sound waves behind it get spread out. And the way that our brains interpret that is the closer together the sound waves are, the higher the pitch of the sound, the farther away that they are, the lower they are. And so when we're standing on this side, we hear the bunched up waves, and that causes the pitch to be higher. But when we're standing on this side, we hear the spread out waves, and that makes the pitch sound lower. Okay, so what does this have to do with galaxies that are far away and moving away from us? How does this help? Well, to get there, I'm actually going to show you a real quick, this is a webcomic, but the idea is solid. If you've done chemistry, you've probably heard of a spectrograph before at some point. What's a spectrograph? A spectrograph is just a special kind of instrument that figures out how bright light is in a bunch of different colors. Right? So it looks at each individual little color of the light, and it figures out how bright it is. And if you pointed one of these things at the sun, which we've done many, many times because we like to do that, it would look something like this. The sun shines in all of these colors, but for some reason there's these lines, these vertical lines of darkness. And as you can hopefully see from this comic, which is basically correct, is that each of those lines corresponds to a different kind of atom. For some reason, atoms out in not just not out in space, but here on planet Earth, only like to grab certain kinds of light. And so when the sunlight is traveling, it runs into something, and sometimes it just keeps going, but other times it gets sort of sucked in by that particular kind of molecule, and it creates these very distinct lines. And the nice thing about these lines is that the pattern is always the same for a particular kind of molecule or atom. The pattern is always the same. And so when we're looking at objects that are far away, we can tell what kinds of atoms and molecules are in it by looking for these lines and looking for this particular pattern of lines. But there's a twist. And the twist is this. Do not want that. Is that if the object is moving away from us, the lines will be moved. It's the same pattern, right? If you look at the pattern on the right, it's the same basic pattern, but it's been stretched out. Just like the car that's going by, it's the same thing here. Light is a wave. The same thing happens. It gets stretched out. So we see the pattern, but we see that the pattern is not in the place that we would expect it. Maybe you're starting to see where this is going. If you point one of these spectrographs at a very far away object, like a galaxy, you'll see something like this. You'll see all these colors, you'll see all the lines, but they'll be in a different spot. Now, this is actually, this is an example from my own research. It's not quite as pretty as this one, but this is a galaxy that I was looking at. This is what a galaxy looks like if you look at it through a spectrograph. There's a lot of just random jumps in there, but you'll notice, let's notice something, is you got, these are the easiest ones to see. You've got these big dips here, right? You got these big dips. Those are some of those lines, but they're not where they're supposed to be. They're supposed to be over here somewhere, but for some reason they're up there. Like I said, this is an actual galaxy that I actually am trying to learn some things about. Because the lines have been shifted, we can figure out that the galaxy is moving away from us. And the wild thing is, we pointed one of these at a lot of galaxies, like literally millions of galaxies that we've pointed one of these spectrographs at. And almost every single one of them, with very, very few exceptions, is moving away from us. So, and what we also find is that the farther they are away, the faster they tend to be moving away from us. So we have this wild fact. We have the fact that first off, the fact that there are millions of galaxies was mind-blowing 100 years ago. It's maybe a little bit less mind-blowing now. It's still a little bit mind-blowing. But there are millions of galaxies. They're very far away, and they're all moving away from us. And that is how we know the universe is expanding. One of the ways that we know the universe is expanding. Right? Again, do you need to know this? No, but I think it's interesting. So the universe is expanding, which, again, was not expected at the time. In the early 20th century, most physicists who were thinking about this, including people as famous and as smart as Albert Einstein, thought that the universe was basically just sitting there, not doing anything interesting. And what we discovered in the last 100 years was that it was, in fact, the case that the universe is expanding. Albert Einstein, to his credit, despite believing deep down to his core that the universe was not changing, or not getting bigger at least, recanted and said, and once he saw the evidence, he was like, okay. The evidence was too overwhelming. He couldn't ignore it, which is good. That's the goal of science. Unfortunately, some people are not always that willing to change their ideas about the way the world works, even in science. So that is all I have to say about galaxies for now. Maybe we'll talk a little bit more about galaxies before the end of the quarter. But we're going to go, oh, right, not yet. So what I want to talk about next, I want to talk about the take-home assignment that I've been talking about for a couple weeks. I'm going to show you something that I'm going to post on Canvas later today. It's, I might make some slight changes between now and then, but the basic idea of the assignment is going to be the same. So there's a lot of text here, so I don't want you to worry about it too much. The main thing I want us to focus on is the goal of this assignment. So what is the goal? The goal is to give you the opportunity to use your knowledge of physics to explore the world around you outside of the classroom setting, right? So in this course, we spend a lot of time in here. We do quizzes in here. We do DL material in the DL classroom. And we don't often get the opportunity to talk about or just see physics in the everyday world. So two things that I want to say before we talk about anything else about this assignment. Number one, it's not designed to be some big, long assignment that you take. It is a written assignment, but it's not something that you want to take too terribly long. Notice, length is like 1 page to 2 pages, single-spaced. So that means if you fill up a page, you're good. Right? You have 2 weeks, it's 1 page. The most amount of time I want you to take on this is 2 to 3 hours, maybe less. Right? If you're past 3 hours, you're doing too much. That's not the goal here. I'm not grading you on your writing style. This is not an essay. It's just an opportunity for you to find some physics out in the world and tell me a little bit about it. That's all that it is. Right? So what is the goal? It needs to include a few things. It does need to include a few things. It needs to include a description of the system that we're talking about, or your observations. A description of the physics principles you can use to describe the system, like conservation of energy, a little bit about that. 1 or 2 relevant equations you might use to describe the system, not in sort of gory detail. You don't need to plug in numbers. You don't need to do any of that. But something like this, right? You're like, oh, I have a system that is open where thermal and bond energy are changing, so this is what the equation might look like. And a description of 1 or 2 things going on in the system that you can't take into account. Maybe because you just don't know the physics. Maybe because physics doesn't have anything to say about it. Stuff like that, right? This assignment is intentionally very, very open-ended. I do have some examples of things that you could pick at the bottom. There's only one rule, which is that the system that you pick cannot be one that we've explicitly studied in class already. It has to be something new that you find out in the world. Again, this is not designed to be something that you spend a ton of time stressing about. It's not something where I want you to write it and then go back and rewrite it and make sure everything's worded correctly, none of that stuff. I just want to see you go out into the world and find a little bit of physics and talk to me about it. Normally this class has 5 quizzes. We're doing 4. I'm hoping that this will take and again, it's 2 to 3 hours max no longer than, I don't know how long you spend studying for the quiz, but hopefully, it's a reasonable trade. Okay? And again, if you follow the instructions and you take the assignment seriously and do actually try to find some physics, you're going to be fine, right? So this is the plan. I will post this later today. Of course, we have another quiz coming up next week. It's not going to be due for 2 weeks, so it's going to be due 2 weeks from today. And what I want you to do between now and next week, I don't want you to put a ton of time into it these next couple of weeks because, I don't want you to put a ton of time into it this week because I want you to have the time to study for the quiz. How I would recommend spending this week is just keep an eye out. Just keep an eye out. Just maybe whatever you're doing, you notice something in physics, maybe make a mental note of it, write something down, maybe think about it a little bit. I will post a rubric and some examples next week after the quiz. So rubric and examples next week after the quiz, okay? Again, this is not designed to be something that I want you to stress about a ton. I just want you to go into the world, find some physics, and tell me about it, okay? So that's the take-home assignment. Like I said, it will be due 2 weeks from today. You can start working on it this week, but I would encourage you to spend your time prepping for the quiz and then do the bulk of the writing. Again, I want you to just spend a couple hours in one afternoon just writing something up. That's all. All right? Sound good? Any questions about this? Again, I will post this with all the details on Canvas later today. All right? Cool. Okay. So let's go back to, not this, but particle model of thermal energy. Okay, so well, now that I'm here, I guess I should just talk about next week's quiz. I will post the practice problems today. As usual, the solutions to the practice problems will be, on Wednesday or Thursday of this week. And this quiz is going to, so our last quiz was on, mechanical energies and graphing energies and stuff like that. This quiz is going to focus on the particle models, but we're not going to do any of the mode counting stuff we talked about here. Okay? So we are going to look at the particle model of bond energy. We are going to look at the particle model of thermal energy, but not counting all the modes, right? So we introduced the particle model of thermal energy last week. We talked about the idea of the thermal energy being split out amongst the modes. We talked about solids and liquids, but I'm not going to ask you to count modes in a gas for next week. I will send all this out again in a message this morning or early this afternoon. Okay? So that's the plan for next week's quiz. And then that's quiz 3 of 4, so we're almost there. Okay. So we've spent all of this time on modes, and it might seem and this is one of the big reasons. Let's think about heat capacity as we thought about it at the beginning of the course, right? Heat capacity was the heat capacity of a substance or of a system was just a number that had to do with how much energy we needed to put into the substance in order to increase its temperature. Right? How much energy do we need to put into the substance in order to increase its temperature? There's another way of framing that, which is how much does the thermal energy of the substance need to change in order for the substance to change its temperature by a certain amount? Let's start here. So we've seen the top equation before, right? The top equation just tells us how much energy is in each mode, right? It's always the same. It's 1/2 times the Boltzmann constant times temperature. But now let us imagine that we want to change the temperature of our substance. And let's ask ourselves, if that is the amount of energy that each mode has to have, how much energy do we have to add to a mode to increase its temperature? And the answer is that much. If you want to change the temperature of a mode by a certain amount, you have to add this amount of energy, right? You plug in your change in temperature, you multiply by the Boltzmann constant, divide by 2, you get a number. That is the amount of energy that has to go into each mode in order for the substance to change its temperature by a certain amount. So why is this interesting? Well, what does this tell us about substances that have lots and lots of modes as compared to substances that have very few modes? A substance with a lot of modes will require more energy in order to change its temperature by some amount than a substance with very few modes would require. Because we have to put this much energy into each mode in order to increase the temperature. That sounds a lot like heat capacity to me. Right? There's this direct relationship between the amount of energy we have to put into each mode, or excuse me, the number of modes that the substance has, and the heat capacity of the substance. About it, I'm just going to show you the top line. You're going to go through and actually figure out where all of this comes from in GL, and like I said, there's a video about it, so I'm not going to talk about it too much here. But let's just imagine a scenario where you just have a substance and you're just putting energy into it, and we ask ourselves, how much will the temperature be by? Or what will the heat capacity of the substance be? Right? So if the only thing that's changing is thermal energy, then the equation up top is something that we've seen before. Right? If the only thing that is changing is thermal energy, then the equation above on the top is something we've seen before. Right? It's a system where thermal energy is changing. That energy is changing because heat is going into the system. But we now have a new way of calculating what the change in thermal energy is. The change in thermal energy is equal to the total number of modes, which is this piece right here. This, the hashtag sign times delta n is the total number of modes in the substance. Excuse me, the hashtag sign times n. It's the number of modes per particle times the number of particles. And then the 1/2 times the Boltzmann constant times the change in temperature is the change in thermal energy for each mode. So we now have this way of calculating the total change in thermal energy. And what do we know about heat capacity? We know that heat capacity is the amount of heat you put into the substance divided by its change in temperature. We maybe have not said this explicitly, but this is what heat capacity is. It's the amount of energy that you put into the substance divided by the change in temperature. And we now have a way of calculating it, and we end up with this. This is a model for heat capacity. It just says that the heat capacity of your substance is going to be 1/2 times the number of modes in each particle times the number of particles times the Boltzmann constant. For 1 mole, we'll talk about this more later. But for 1 mole, in other words, for Avogadro's number of particles, you end up with the Boltzmann constant times Avogadro's number. This is a new constant that we call R. If you've taken some chemistry classes, you've probably seen it. It's called the ideal gas constant. Preview of what's coming next in this course. It's called the ideal gas constant, and it's just a number that shows up. So for 1 mole of a substance, we can calculate the heat capacity like this. Just 1/2 times the number of moles per particle times R. But again, where does this come from? The place that this comes from is just thinking about the fact that if we want to change the temperature by a certain amount, we have to add enough energy to each of the individual modes. And so the more modes there are, the greater the heat capacity. Okay, so the last thing I want to talk about today is this freezing out of modes. So we just found this equation right here. The heat capacity for 1 mole of a substance is this number. So let's go back to carbon dioxide, the case that we saw earlier. We learned how to calculate the number of modes that carbon dioxide has, and we learned that a carbon dioxide molecule on its own in a gas is going to have 13 modes. Right? And so you would do the very natural thing here. If I were to say to you, let's calculate the heat capacity of 1 mole of carbon dioxide, you would plug 13 into the equation that I said should give you the heat capacity for 1 mole. You plug 13 in here, you multiply this out, you get about 54 joules per Kelvin, right? The way we interpret that is to increase the temperature of 1 mole of carbon dioxide by 1 degree would require 54 joules. So you would calculate this, and you'd be like, okay, well, this seems to be good. But if you actually put the carbon dioxide in a calorimeter, or whatever it's called, and did the calculation, did the measurements, you would get something very different. The number that you would get would be about 34 instead of 54, which is pretty far off. There's something missing. There's something that we didn't get quite right. If the real number is 34 and our model says 54, that's a little bit too far off to be comfortable. So what is it? And what it is this, is that sometimes certain modes in a substance just will not be available. So if a mode is a box that we can put thermal energy into, a frozen mode, or a mode that is frozen out, as we like to say, is a box with the lid closed and a lock on it. And for some reason, that is perhaps a little mysterious. And it will remain a little bit mysterious because we just don't have time to talk about it. But for some reason, if your substance is too cold, certain modes will be available. They'll be locked. And in this case, we say the mode is frozen out. We say the mode is frozen out. So you can see this on this plot, which you'll see more in GL, but it just shows you the heat capacity of substances in terms of their temperature. And what do we notice? We notice that as the temperature increases, the heat capacity of a bunch of these substances goes up. Right? Why is that? Because you have all these modes that were not available that are becoming available as the temperature increases. As temperature increases. Now, so then, what was the point of spending all this time learning how to count modes if I'm telling you that it doesn't work quite right? The number that we calculate from that recipe that we talked about is the maximum number of modes that the substance can have. Substance can never have more than that number of modes, but some substances can have less. Now, do I expect you to memorize when certain substances will have certain modes frozen out? The answer is no. So where could you see this in a problem? I might say something like, you have 1 mole, suppose you have 1 mole of carbon dioxide with vibrational modes frozen out. Right? That's what the question might say. Which requires you to know, okay, carbon dioxide has 13 modes. 8 of those are vibrational. Right? 4 potential energy vibrational modes, 4 kinetic energy vibrational modes. So if the vibrational modes are frozen out, then for the purposes of this problem, my carbon dioxide only has 5 modes. Usually it would have 13. The 8 vibrational ones are not available, right? They're a box with a lid on the top, right? Locked. They're just not available. And so you would not consider them in the problem. And so for our purposes, when a mode is frozen out, it's like it just doesn't exist. It just doesn't exist. And again, you do not need to memorize when certain modes are frozen out. I will tell you. If you need to know that a particular type of mode is frozen out, I will tell you. But remember, to use that information does require that you know what kinds of modes you have. Because if I say the vibrational modes are frozen out, then you will need to know how many vibrational modes there are in order to do any sort of calculation with that information. Okay? We will talk about this more in GL. All right, let's call it there. Have a good rest of your week, everyone. Take some time off, hopefully. If you're looking for something to do, and you're into this kind of stuff, last week I saw Everything Everywhere All at Once. Really, really, really good. You all should go see it. It's awesome. If you get overstimulated by like really chaotic scenes, maybe wait till it comes out on streaming, but it's really, really good. Worth your time, in my opinion. If you're into sci-fi, if you're into like absurdist humor, stuff like that, it's great. All right. Have a great week, everyone. I will see you next week, or in my office hours today.